So here's the second programming assignment, and it's fine if you just use your first programming assignment in code, but you'll have, as a structure, but we really are looking at something different. And we've chosen to look at this partial differential equation. So this one, you might look at and say, well, this has nothing to do with fluid dynamics. Or maybe it does. And you can see that there's a partial u partial x. So we're looking to solve for u. Right? So u's are unknown, and we're in domain x and y. And we are going to solve this problem using a technique called spatial marching. And you might look at this equation and say, oh, Professor Miller, you probably can't do that because it's these types of flows and corresponding like model equations are elliptic, and you would have to use like an iterative solver. It is a linear equation, you can see, so we could use like algebraic solver, like a sparse matrix solver, approximate the differential equations. But when we turn it in the future and modify this equation into a more general laminar flow solver, it'll be nonlinear. So there'd be no point in setting up a linear algebra solver for this case. But we use linear algebra. Anyway, let's finish defining the problem. We have some domain, and there'll be like an x direction and y. And I'm giving you some boundary conditions. So I'm saying that u along the x direction along 0 is 0. And there's also some location y equals 1 where u equals 0. Okay, so that's the domain. And then I give you an initial condition. Now, I'm in spatial coordinates, but I'm calling x an initial condition, which is usually time in, say, CFD. So this is what? This is a different y, so this is u of 0, comma y equals 0. And, of course, and here's something I don't know. And you also notice for this problem that it'd be very typical to specify the right boundary condition. But if we were in a boundary layer flow, we would normally know what's happening upstream and we would march downstream. So in the future, we would be changing x to t, and we would leave y as it is and add a viscous term to the second derivative, just like the Navier-Stokes equations has a second derivative. The right-hand side source 1 could be seen almost as a pressure gradient. What would be missing from this equation, of course, is a term like, say, u partial x, which is the nonlinear term on the left-hand side of the momentum equation. So we have a single PDE, which is sort of like a model equation to develop a general solver for laminar flows. And I have shown, through a little bit of effort back in December, in my office, the analytical solution, which I think is rather elegant, and I've just written it out for you. And it involves u of xy, so you can set xy anywhere. If you want to evaluate this numerically, you would have to actually plot it, and you'll have to, for your homework, the summation of k equals 1 to infinity. And in the numerator, we have -2 cosine k pi. So k is almost like a kind of like a wave number for in space, right? Because you're going over k. And we have e to the negative k squared pi squared x. In the denominator, we have k cubed pi cubed times sine k pi y. So if you can learn a lot physically about things if you have an analytical solution and about this PD. If I look at this term sine k pi y, you can see that goes from, say, 0 to 1, and there's a pi term, so if k is, say, 1, then it's the sine of pi y from 0 to 1. And that definitely enforces my boundary condition from 0 to 0. So you can see just, if you look at the equations from a physical point of view, that absolutely enforces the boundary condition, which is here. And then I have initial condition. So if I set x equal to 0, well, this term doesn't matter. But if x equals 0, I would hope that this type of term goes to 0. So that's the exponent of -0, so that should go to 1, and 1 minus 1 is 0. So that term is partly there. You can see physically you enforce the initial condition at this location. And of course, as I go downstream, you can learn things about the solution. X becomes bigger, then this term, I believe, would be a little bit positive always. This is like a Gaussian term. It would probably look something like this. Gaussian. And then this term here, well, you'll see what happens when you look at the solutions. And so let's just leave that there. So the object here is if you develop a solver, you want to validate it and make sure it's working, right? Anytime you program a CFD code, how do I know it's correct? Obviously, if it solves the governing equations, the original PDEs, if they're consistent with the discretized form. But even better, I can compare it with the actual analytical solution. So this is a great thing. In laminar boundary layers, there is an analytical solution, which is called the Boussinesq solution, right? And so in the third computer project, when we turn this into a laminar solver, you have an analytical solution, which is the Boussinesq solution. Now, when we take the laminar flow solver in project 4 and add in a turbulence model, we would have a turbulent flow. There's no analytical solution for the turbulent flow. That's why we showed all these empirical composite profiles at the turbulent boundary layer. We would compare it with the log law of the wall. So the nice thing about this solver right now is it's like a linear PDE, which is like a representative equation for the laminar solver. And we need to get our solver running and working correctly and validated with this analytical solution before we turn it into a laminar solver. And this is often how I trained students coming into NASA, and a lot of students here over the years, undergrads and grad students, that we build up a solver and validate parts into something more complicated. And I think it's a good strategy. It's like divide and conquer. So then I say, well, we're going to solve this equation. I give the analytical solution. We want to find it numerically, just like we would for a CFD, full CFD code. And we're going to restrict it to this domain. So y is between 0 and 1, and x is greater than or equal to 0. And we're going to basically start at x equals 0 and do a marching technique downstream. So you could say, well, I could just, basically try and set up boundary conditions and solve this analytically, because I know the analytical solution, so I could actually form the boundary condition on the right-hand side. But you don't really know that at all in a turbulent flow solver, because that's really what you're trying to do, is solve for the profile downstream. And that would actually be more computationally expensive than just doing a marching method or what some people might call a shooting method if you're matching something downstream. So anyway, the bottom line of the assignment is to try and solve equation 11.7 using the Crank-Nicholson marching scheme. And that's a little bit different than Runge-Kutta because it has better stability characteristics. Raise of hands, how many people have seen Crank-Nicholson? 1, 2, 3, 4. Wow, half the class. That's amazing. So I actually, this weekend, I pulled down Crank-Nicholson original paper. And it was actually written, I forgot what year it was, 50s or 60s. It's a pretty new numerical method when you think about the history of numerics. And I put that on the class website. You're not required to read it, but it's there. And I think it's just really interesting to read a paper like that and see what they were thinking. So I read through that on Sunday and really enjoyed it. So, check it out. And we want to construct, using Crank-Nicholson, a so-called diagonal scheme using the central order differencing in the y direction. So that's a little trick. We're going to apply Crank-Nicholson on du dx, and we're going to apply our second order differentiation, discretization, on the second order term d2u dy squared. And it's just like the first assignment. I think I glanced at a few people who turned in already. One page is fine, just concise is nice. I don't want you spending your whole life, right, kind of reiterating what I'm saying. I want just a description of the problem in your own words, the equation we're solving, just re-describe the numerical approach. This isn't really a formal net proof. Maybe I should have said comparison. And what does that mean? To demonstrate convergence. Well, to demonstrate convergence in this case, I would maybe use a grid independence test, right? So in my initial grid, I might say have, I don't know, what do you want? 500 grid points in the y direction, and say 1,000 grid points in the x direction. And now I double the number of grid points in each direction, and I run my solver again, and I would compare the two solutions. The two solutions should be the same. So that means the more grid points I add, the smaller dx dy, I have no change in the solution. That proves to me that, well, not proves, but it's a very good indicator, the easiest one, that my solver is grid independent. And when you write your solver, you should have like a dx and dy variable, right, which you can easily adjust. Anyway, if you've done that, that's good. And then you can discuss the solutions, the ones I asked you to plot here. And I'll show you my solutions in a second, just so you know what you should be looking for. I would like you to try and derive the analytical solution, just one attempt. And if you can't do it, that's okay. Just show me your work, as that's harder than doing numerical stuff. Like, why do we do numerical things? Well, one reason we do numerics is because most people aren't smart enough to solve the partial differential equations. In fact, I don't know anybody who is. And we don't even know if they're solvable. And the second reason is it's just easier to do numerics, and they give us practical predictions. Anyway, I'm asking you to make the following plots: y versus your numerical solution versus your analytical solution at 0. So your numerical solution is an analytical solution, or just the initial condition. Okay, and then you do y versus numerical and analytical at 3 axial locations in the x direction. So here's your flow, right? So you're doing x equals 0.25, and 0.1, that's up in there. And I do down here at 1.0, which is sort of like at the end of the domain. So it's a marching scheme. Okay. Once again, just copy and paste your Python, C, Fortran, MATLAB code, whatever. And I really prefer you don't use libraries. This can easily be programmed. And I was going to choose a 5th order spatial scheme. And I said, wow, then your linear algebra solver has 5 diagonal bands. Does everybody know what I'm talking about when I'm talking about linear algebra solver? Okay, so this time you'll get 3. So to get to equivalent solutions, you'll have to use way more grid points because you're having a lower order code. Okay, and also if you did 5th order spatial integration and you did a 2nd order spatial marching scheme, your whole code would reduce to 2nd order. There's no point. So then I would have to say, oh, I have to ask my students to do like a 5th order implicit spatial marching scheme, and it's not worth it because our computers are so powerful now, we can just add grid points, not worry about high spatial accuracy. Okay, and then of course these plots which I described. So let's look at some of my notes, I guess. Wait, these are, how do I want to do this? Do I have another? Well, okay, we'll just look at what I have. These are just, this was like a draft. Okay, yeah, this is what I wanted to show. Sorry about that. I also had a printout. So once again, solve the equation. Here's the boundary condition, initial condition, 2nd order Crank-Nicholson scheme, tridiagonal band solver for marching in the x direction. Domain is from 0 to 1. And we have to discretize this term, right? d2 dy squared, that's right here. So here's your standard finite difference 2nd order scheme. It's central. So in this case, see, I say uj plus 1 plus uj minus 1 minus 2uj, so that's central. So let's just, if you have 3 grid points in the y direction, this is your j location, this is j plus 1, and this is j minus 1, and then there's your delta y. So that should take our continual term, the 2nd term in the ODE, or excuse me, PDE, and discretize it. So we handle that. And if you look at Crank-Nicholson's paper or any contemporary documentation on Crank-Nicholson, I've also given you the Crank-Nicholson discretization scheme. And it's a little bit interesting. And I've discretized equation 11.11 for you right here. So here's the term on the right-hand side, it's 1. And I have an implicit first order term for d dx, but the whole scheme's higher order second. And here's my two spatial, cross-stream terms. So see, there's dx. So if I have grid points in the x direction, this is delta x. And we might have, say, for instance, I here and I minus 1. Okay. So what does this mean? This is d2u dy squared at I plus d2u dy squared at I minus 1. So we'll take this term and evaluate it at, say, I minus 1 and put it in here. And we would also set I equals 0, for instance, or just leave it as I, and that would be the first term in here. Okay? So what do I do now? When you set this up, you'll see that you indeed get a tridiagonal system, and you can easily just do one backward substitution, basically, and find the solution at each I grid point in the x direction. And there's different ways to do that. I have used the Thomas algorithm. And if you want to read about it in terms of, like, say, Python, it's described at this link. And you can just Google that, or you can always take a picture on the board to grab it. Okay? Anyway, you can now take this equation 1115, rewrite it as 1116, essentially, same equation. And now I multiply both sides by delta x, and now I have delta x plus delta x over 2 times basically the averaging of the cross-stream second order derivative. And I do a little bit more work, and I move delta x over 2, see this term here, with I to the left-hand side. And I keep everything on the right-hand side as I minus 1. So you see here's I and I minus 1, and I minus 1. So this way, at least, I have, I can keep all my unknown data on the I grid point, and I know all my data at the I minus 1 grid point. So when you start your solver, your initial condition would be I minus 1, which would be the first grid point. First grid point in your marching direction, right? And then you march to the grid point I, and then you update your solution from the new solution to the old, and you reiterate and go through the loop. And you keep doing that through all your little dx's and using the Thomas algorithm to solve the resultant triangle system until you get to x equals 1. And you're done, hopefully. Okay, so let's look at my solutions to see what might come up. So this is kind of what you should see. So this is at x equals 0, right? So this is the initial condition, and I wrote the initial condition as u equals 0. And of course, if you evaluate the whole analytical solution, don't just plot 0 for analytical. You just program the general analytical equation and call that function, if you make it as a function or subroutine, with x equals 0 and vary y. And it should give you 0. That's a nice way to confirm it. And here's y from 0 to 1. And I graph my numerical solution, which is actually just the initial condition. So this proves to me that I have the initial condition in the code in memory correctly. That's really important. And I've wasted so many months of my professional research career using wrong input data. Because I thought I was smart and got a little cocky, if you will, and said, oh, of course it's correct. And then like a week or two later, not getting correct solutions, I look and like, oh my God, I got the wrong initial condition or boundary condition. So that happens to everybody. Hopefully you can learn from my mistake. Anyway, I plot the numerical and analytical solution. Okay, so let's see what happens when we move downstream. This is now only at a x equal 0.10 meter, that's 10 centimeters. Same type of plot. Y-axis from 0 to 1, right? So there's our boundary. And x-axis, I plot u. And this, there's no real meaningful units for u, so I just wrote as meters. You can write meters per second. It's sort of like an undefined quantity because it's just like a, not a physical equation. It's just an equation to solve for u. I guess I could write meters per second. That might be just a little more meaningful. And you can kind of see, you could imagine it looks very similar to a laminar boundary layer, but it's not at all. Remember, it's just a linear equation. Of course, laminar boundary layers is a solution of a nonlinear equation. So don't be fooled, right? This is not a fluid dynamic solution, but it's very close. And you can see that very quickly, the magnitude at the peak in the center of the channel, if it is a channel, has gone to about 0.075 in only a tenth of the domain. Let's march downstream even further. Remember, it's a marching scheme. Yeah, I'm glad that was there. Oh, I didn't show the intermediate solution, but I got all the way to the end of my channel. So this is at x equals 1 meter. So from 1/10 meter is 0.075. Now the magnitude's about 0.12. And you'll notice another thing that's nice is I've enforced my boundary conditions, right? So there's 0. So that's one thing I always look for. That better be 0. And in the center of the channel, I have symmetry. So if we have a steady boundary layer flow, it doesn't matter if it's laminar or turbulent, and I plot the solution in the cross-stream direction, and I have a symmetric boundary conditions, right, I should have a symmetric solution. So if your solution's not symmetric, that's an easy thing to check for right away. And also the magnitude's much higher. So these are the solutions I got, and I plotted numerical versus analytical, and I did not go to the further step of saying, oh, calculate L2 norm or other errors. Plotting it like this is fine. But it's probably good practice in your own careers to plot, errors between analytical solution and numerical solution. So this is just from a function call, okay? So what would the order of the error be, like an L2 norm between the numerical solution and the analytical solution for these types of solvers, if I've done it really well? I'm sorry?
Really small.
Yeah, really small, but I mean, small is different, like in our world and like a computer world, right? So machines have precision. And we have 64-bit processors everywhere now, and you can use high order precision, and you should get something on related to the precision of like the amount of memory you're storing each variable in, right? So the error could be on the order of 1 × 10⁻⁸ or -16th, depending on if you're doing things really well in single or double precision, like if you use Fortran. That's the nice thing about Fortran and C, you can really control the amount of memory you're storing variables in, and you can kind of look for that type of error. Anyway, that would be like going beyond the call of duty, if you will. How would I do this program in the last little bit of this? We have a short class today, which is nice. How would I do this program? Well, I would probably initialize my variables, just so you get an overview. So I'm kind of doing it from a Python or Fortran perspective. Check out my program here for a second. Don't miss any of my steps. And in Python or Fortran, you'd have to do that either way. In Python, I actually imported the numerical Python or NumPy library, and I made these plots with scientific Python, so I imported those libraries. And what I did is I defined a function, and you do that different ways, right? For different languages, your choice. In Python, I do those up front near the first beginning of the program. I don't put them in like an extra file. And I just defined my d2y d y squared function. And that had a few arguments. It had basically u of I minus 1, u of I, and u of I plus 1. I and j are interchangeable, it doesn't matter. And I had h. And h was my grid point spacing delta y. And so every time I wanted to calculate the derivative, I just called the function with the appropriate values of u at the known initial condition. And then after I defined functions like that, what did I do? I defined my, say, number of grid points, right? That's probably important. And for me, the base number was 501. And why did I choose 501? So I have a nice even grid point spacing between y equals 0 and y equals 1. Right? So if I take 1 and from 0 to 1 and divide by 501, I get nice even spacing. And then I set values of, say, like x max, y max, because maybe I wanted to vary y. So I set that to 1, and this maybe like 0.1. And I ran my code, and it just stopped at 0.1. You can run your code from 0 to 1 and export variables or make contour plots or whatever you want. So that's basically how I did that. I set delta y this way. Delta y equals y max divided by my number of grid points minus 1. And that gave me a nice grid point spacing. And I set dx equals dy over 2. Stability. So you don't have to do any stability testing with Crank-Nicholson. As I kind of gave you a little hint there. Dx I just set to dy over 2. So see, I calculated my dy spacing, let dx be over 2. Okay, those are important things that I want to note. Oh yeah, after I set up all my functions and set up all my data, I echo it. And I take all the variables I created in memory, my initial condition, and I write them all to file. And that's what I was talking about learning lessons at NASA the hard way. I write every variable that I loaded from files or created in memory to files. And I put it on the screen and I put it as an echo.txt file. And I open that and I look at it. And that way I'm absolutely sure that I set things like, pi right or other functions or whatever. And I absolutely know my initial condition. So you can also export your initial condition right away. So that's what I do. So I have statements like, just an example. In Python, I would write print. I would, do like, I don't know, let's see, dx. And so on my screen, I would see the variable dx and I would see the numerical value. I would just do that for all the variables, no problem. And then the solver, that's the hard part, and I'll give you my general solver. Well, I would first want to go with the initial condition and try and set up my A matrix and B matrix. So I would do that by setting my A matrix, which is stored. If you write this out, you'll see that it's stored as like 3 bands. Well, in memory, I would store that as maybe an array of, say, A of 3n, where n is the number of rows. Since I have 1 PDE, I would have 1 row per grid point, right? And in a laminar boundary layer flow profile in compressible, I'm solving the D'Alembert condition and the momentum equation. So I have 2 rows per grid point, right? So think about that for the future. You're going to have to take this and generalize it in the future. Anyway, I go through, and using my discretized equation, which I showed, I would fill in the values in my bands through a loop. And those coefficients are based on my discretization. So here's a question for you. What do I do at, say, n equals 1 and n equals n? Or, excuse me, like if this is 1, and this, let's say my number of grid points was what, 501? So we'll just say 501, for instance. What would I do? Those are boundary conditions. So in A, I would want an equation here that would be like, what? 1 times the value of u at, say, 501, if that's my maximum grid point, equals what? My boundary condition, 0. Up here, in the first row, I would want to overwrite my definition and say maybe 1, which is the diagonal A at this location, times u of, say, 1 equals 0, right? And that 0 comes from the right-hand side B, right here. And all these terms here is the right-hand side terms. And you can see I have a source. What is my source? My source is 1, right? Which is kind of like partial P partial X. If I had a pressure gradient equivalently. So that would be the right-hand side source. So the right-hand side is really easy to create. I just set my first array element to 0, excuse me, and the last one to 0. And I would move all my known terms to the right-hand side, so that would be not only the source term, but I formulated it like this, and you can check my work, but I kind of checked it by analytical solution. So I looped over j min plus 1 to j max. And in Python, unlike Fortran, this is really annoying. This loop, this for loop over j, this is really one value less than array minimum. I hate that. That's one of those things in Python which was not developed very nicely for someone doing numerical solutions. Anyway, inside the loop, I would say b, right-hand side, that's my variable of, say, j, equals u of m minus 1. I used a different index. I used m of j plus dx over 2 times my function, partial derivative function. I'll just call that d2y squared of um minus 1 of j minus 1, um1, and um1 of j plus 1, and finally my grid point spacing dy. So this function here, this is the name of the function. I just wrote d2 dy squared. That's um minus 1 at j minus 1, um of 1, and m minus 1 of 1, or excuse me, j, that's a j, and u of m minus 1 at j plus 1. So in my code, for some reason, because I was looping over i's and j's in my loops, I call my indices m and m minus 1. So see, this is my known solution. Okay, so I'm calling this um minus 1. That is the known initial condition, or whatever is happening at grid point m minus 1. I'm trying to solve for grid point m. That's why everything in array a x equals b, everything in A is really operating the coefficients for unknown variables um. So this x here of A x equals b, this is on, say, um, and this is um minus 1. Okay, so I've set up the coefficients A, and I have a right-hand side B, and to march 1 dx, I have to what? I have to, of course, solve the system ax equals b, and I go to the next grid point, and I keep looping over that, and I have a little check, and I was smart enough to set dx to be some, if I add a bunch of dx's up, I'll get a value of x that I desire, right? I won't have to make a fractional step, which is annoying. So it's smart to choose your dx values as some, integer fraction, if you will, of whatever x should be that I want. And then I just keep looping with a while loop over that whole system until I get to the location I want. And that would be where in my loop, and you just do u minus 1 equals um, right, after I solve. Right, that's an important step, to overwrite um minus 1 equals um. And then, of course, I write this to file. Or if you're in Python, one of the good things about Python, if there is something, is that you can use something like the scientific Python library, right? And you can use commands like plt.save fig into output.pdf and format equals PDF. So that way I have a nice vector graphic which journals accept. There's no point in making JPEG graphics in your career, because if you are lucky enough to publish your results, your journals are going to ask for EPS or graphic figures. So that's a good habit to get in. So I like EPS or PDF. That's really up to you. But that's a big overview of my program. So I did a lot of the talking here, and now it's your turn to ask me questions. about anything that I might have missed. Anybody has any questions? We'll just wait a second.
How many terms in this analytical solution do you usually use?
That's a great question. So let's scroll way up here to the analytical solution. And I love this question because, analytical solutions like this, and this is a really, I guess it could be complicated or simple just depending on your point of view, right? Some analytical solutions could be pages of material generated by like a computer-aided mathematics program like Mathematica. So this one's simple. And your question, just to repeat it for my computer in the class, is, how many terms maybe do I let K be? And that's part of the fun too. Like, for example, I could set K to be from just 1 to 1. And that probably wouldn't be enough. And ideally, I would set, sum over from K equals 1 to infinity. But why don't I do that? Well, 2 reasons. One, it would take infinite time, because it's an infinite number of operations. So that's one reason. Another reason to have finite K would be computers, obviously you're only going to hold so much data, and for very, very high values of K, I wouldn't be really adding anything to the solution. It wouldn't be changing. And the additional values of K for like K equals, 100 billion Google or whatever, it would look like the same, and the numbers in the computer wouldn't change. So that's a finite number which is too high. So then I say, okay, well, how do I practically evaluate the summation to my satisfaction? Well, first of all, you can always graph it, right? And it would look weird. It has some strange oscillations for low K. On the other hand, there should be like more of a quantitative way to find K, like for K max, K equals 1 to K max, for instance. So with all that in mind, like, what's a good quantitative way to do that? And I just talked about machine precision. And I could do it through like trial and error. I could just keep increasing K max and looking visually at the solution until it stops changing. That's not a very satisfactory way, because it's not quantitative, it's just visual on a computer. And so maybe Alex, you were adjusting your mask. I didn't know if that was a question or a mask adjustment.
Yeah, no, I was raising my hand.
Okay.
So, if you know the analytical solution has a maximum value at the center line, you could just compute the value of K for which that exponential term will probably fall below some precision.
Yeah, your idea is really interesting to me, that you would say, okay, I'm going to look at the centerline value, and I kind of know what it is by simplifying the analytical equation even more. And then if I'm hitting that with my numerical evaluation of the analytical solution, then I'm done. That's a pretty unique idea. I really like it. Though it is a little bit problem specific. Like, what if the analytical solution was so complicated I couldn't do much analysis on it? And that's definitely possible. Like, analytical solutions, if they exist, might just kind of be beyond our comprehension. So I would think of it, I would test my analytical solution in a way that I would test a general CFD solver. And I could like double the number of K max values and look at the change or residual of the solution with doubling of K. And if the doubling of K results in the same value, or a change of value which is less than machine precision, then I would stop. And that technique, I think, would work for any type of evaluation of an analytical solution. But I like your idea because it's elegant. And there should always be bonus points in universities for elegance. But industry doesn't care much for such things, I think. So, unless you're Kelly Johnson at Lockheed Martin or something. That's a really great question. And I think it like brings up a lot of interesting points about, evaluating solutions with computers if they're analytical versus numerical. So, great question. So everybody's comfortable with discretizing with Crank-Nicholson, forming AX equals B, doing a back substitution, triangle system, and doing a grid independent study, evaluate your analytical solution as a function. and checking if it's converged, if you will. And we'll go from there. And I think it's really important to try and get this solver working, because we're going to take this and modify those equations to solve the laminar flow equation with a little bit different boundary conditions. Okay. All right, well, thanks a lot for your time today. I really appreciate it and hope you have a great week.